So in the movies, you see it all the time. You know, people want to go to the future, so what, they build a time machine. You just press a button and boom, you're in the future just like that. Well, I'm here to tell you that we can't really do it like that, but we can go to the future. Now, to go into the future, we have to accept two truths. One of them is that the speed of light is always constant in all frames of reference everywhere. The speed of light is 299,792,458 meters per second, or 3 times 10 to the 8th meters per second. Now, as Americans, we can't really grasp how fast this is. So, in miles, it is 186,000 miles per second. Per second, not per hour, per second. That's pretty fast. Now, accepting this first truth, we have to accept another one, that time isn't constant, that the rate at which time passes can be changed. Okay, so if we have these two truths, we can move forward. Now, there's two ways in which we can change the way time passes. The first is called gravitational time dilation. Gravitational time dilation is based off Einstein's theory of general relativity. This is a bit too complex to cover in a 5-minute TED Talk, so we are not going to delve into this topic. We're going to go into another one called relative velocity time dilation, which is based off Einstein's theory of special relativity. This topic is by no means simple, but it is simpler than the gravitational one. So this is the one we're going to pursue. Okay, so to come up with his theories of relativity and whatever else, Einstein used thought experiments. Today we're going to use a thought experiment to understand this topic. Okay, so now imagine we have a rod which is 186,000 miles long. Just imagine, it's a hypothetical situation. It's probably never going to happen. Now, we know that the speed of light is 186,000 miles per second. Therefore, to get from one end to the other, a light particle would take exactly 1 second. This is known as a light clock. And this is the way we measure absolute time. It never changes because the speed of light is always constant. Now, if we set a light clock in motion, you can see that it would actually take longer for that light particle to get to the other end because it would have to travel along the diagonal instead of straight up and down. But a light clock always measures absolute time. So in that frame of reference where the clock is moving, time would actually have slowed down because it would take longer for the light particle to travel along the diagonal. As you can see, here, in the absolute frame, the light clock would just travel up and down along this vertical rod. But when the clock is moving, it would have to travel along the diagonal, which would obviously take longer because it's a longer distance. So that is how we can slow down time. Because when you are going fast enough, it would take longer for the light particle to travel up and down along the light clock. Okay, let's take a look at the mathematics behind this. So this is known as the Lorentz factor. It's represented by the sign gamma. The Lorentz factor is 1 divided by the square root of 1 minus the velocity squared divided by c, the speed of light, squared. So as you can see, as we go faster and faster, this entire thing would get larger. Now, why is that? It's because, first of all, as v approaches c, this would reach 1. And when you have a 0 in the denominator, it goes to infinity. Therefore, as we approach the speed of light, the Lorentz factor gets infinitely large. This is a graph representing the absolute time and the time that is passed when one is moving. So, okay, as you can see, as the velocity is the fraction of the speed of light. So as we approach 1, which is the speed of light right here, the t prime up there goes to infinity. That means that even at a fraction of the speed of light, we're slowing down time. Well, how does t prime, the one on the left-hand side, and t work? T prime is considered T prime is the time as one is in motion. So it is the amount of time between ticks on a clock when one is in motion. The other t, the one on the right-hand side, is considered the standard time. So this is the time of an object at rest. This is the standard amount of time that it takes an object, that it takes for one tick to pass by. Now, as you can see, as we go faster and faster, and as t prime increases, for every one tick of t prime, there are several ticks of t that go by. Because of this, time is effectively slowed down. Because imagine a clock that ticks slower than the other clocks. The clock that ticks faster will obviously move forward in time faster, whereas the clock that ticks slower will move forward in time slower. Using this principle, we can travel into the future. So how exactly would we do this? Let's use another thought experiment. Imagine we have a spaceship that can travel 99.9% the speed of light. So we're really close to the speed of light. That means that the Lorentz factor, gamma, as we saw before, is very large. Or as we can see in the graph here, when we're 99% the speed of light, we're approximately here. That's quite large. So for every tick that goes by in t prime, there are several ticks that go by in normal time. Now suppose we take this spaceship that can travel at 99% the speed of light, and we just travel off into space. We would effectively be slowing down time for ourselves, and so the people back on Earth would be going at the normal time. Therefore, they would travel into the future faster than we would. And so when we came back to the Earth, we would have aged less than them. Now, this isn't the conventional way of traveling into the future, but it is a way. Because imagine, if you're going at 99.9% the speed of light, the gamma factor is 31.6. Therefore, for every tick that goes by for us, there are 31.6 ticks that have gone by for the people on Earth. This would mean that we are traveling 2 times slower, and this can have a large effect when it goes by over a period of time. Now, if we were trying to do this on a practical scale, we would need some kind of fuel on our spaceship that we can use for a very long time. Right now, if we use gasoline for this, first of all, it would cost a lot of money, and secondly, we don't even have enough gasoline to propel us to such speeds. So we'd have to turn to some unconventional energy sources, such as matter and antimatter, which provides a lot of energy from a small amount of mass, or fusion, which we are currently exploring as reactors, which are different from our normal nuclear reactors, which are fission reactors. And finally, we could use hydrogen fuel cells, since hydrogen is the most abundant element in the universe. And finally, who knows, maybe we could just come up with some other fuel source to go really fast so that we can travel into the future. Thank you very much.